No, actually the subject of one-on-one algebras is actually quite attractive and it's nice to get to learn. But unfortunately, most books that you see, you will get initially you will get weighed down by pages of this topological vector space kind of very unappealing kind of discussions and computations and so on. But the sense of the theory lies not in all this kind of thing. It is in the rich star algebra structure that you have when there is this compactness that the unit ball has. And the rich structure that the algebra enjoys in virtue of the unit ball being compact. That some things it is closed, and almost anything you want to do, it will be closed under such operations. So because of this compactness, so unfortunately this is something that one has to go through, and so the little pitch I'm making for. I've written a book on one-on-one algebra, but I've tried to avoid all this and straight away get into the nitty-gritty without getting into all those points of topology. But on the other hand, these are things that you have to know. And if we're doing the course properly, I thought we might as well do it the way it is usually done. So which is why I'm subjecting you to all this kind of painful lemmas. Okay, so I'll try to finish off this chapter as quickly as possible, so that we can get on to the next and more attractive propositions. Okay, so see the next. So the next thing on the agenda is this. So you have so you have M, a subspace of B, we will think of B as B of H, as M as a phenomenon algebra. But effectively for this lemma, all you need is that M is a sigma. Okay. B star is a closed subspace and M is sigma B star closed. Such that B is B star star. That is exactly the situation we have. And if you have such a sigma weakly closed subspace, then one wants to say that M itself has a predual. Right? So this is what one wants to say. So the lemma says the following things. Then if you write M lower star equal to the set of all phi restricted to M, where phi is in B lower star. So this is clearly something which is contained in M upper star. And the assertion is that this is a norm closed by this I mean the natural identification. Yeah. And in fact, say it here yourself, and I just say, and in fact, M lower star can be isomorphic to, okay, so what is this? So you take B lower star mod, I prefer this notation, but he writes in the book, he uses the notation M0, where this M lower perp is all those phi in B star such that phi of M equals 0. That is, when I say this, I mean this is Banach space, isometric isomorphism. And the norm, there is an isomorphism, M star can be identified with this quotient space with the quotient norm. And this is what is being asserted. Okay. So, in particular, what this says is that, okay, what is stated as 2 is a consequence of this, and hence 2, if phi is in M perp, in M lower star, there exists, see what does this mean? Actually, okay, there exists and epsilon positive, we call it phi naught in M lower star. There exists phi in B lower star such that phi restricted to M equal to phi naught phi of M perp is 0 and norm phi that is in B lower star is less than norm phi naught plus epsilon. That is the kind of quotient norm. So rather than being mysterious, so let me just get on with proving this. So I don't know if if I do it cleanly, and I'll try to do it, but I was trying to figure out the proof. In the proof that he gave, he uses something called the bipolar theorem, for which you have to go somewhere else to see the thing. So I've tried to work out my own proof. I don't know if it will work, but we'll see how far it goes. Okay, so first I want to note that okay, so see M is a subspace of E star, whatever of E. So I want to look at the map that sends look at the map from E star to M star defined by T of E equals phi restricted to M. Then by definition M lower star equals T of E star. Right? Because by definition M lower star is those restrictions of things from E lower star, and so that is exactly what I'm saying here. Okay, so the first thing that must be clear is that norm T is clearly less than or equal to 1. If you take a linear functional and restrict it to a smaller subspace, its norm is not going to become any larger. Right? On the other hand, I want to say, but on the other hand, what Hahn-Banach theorem tells you, that for all phi naught in M lower star, which is contained in M upper star, whatever. This is after all linear functional in N, so you can extend that to a linear functional on E with the same norm. There exists a phi in E upper star, upper star, so that phi restricted to M equal to phi naught. What do I want to say? Huh? No, phi naught is phi restricted to M is phi naught, and norm phi equals norm phi naught. That is, what this says is that norm phi naught equals inf of all phi in T inverse of M of phi naught of norm phi. Actually a minimum. This says that this is greater than or equal to, but it is less than or equal to because t is norm decreasing. Right, so what this thing really shows is that this says that m sorry, I should have said m. Let me just take phi naught in m upper star itself. Take a phi naught in m upper star, and then one straight away has that you can extend that to. So the Hahn-Banach theorem, I'm using only the norm space version, not the topological locally convex version. Okay, so one has this, that is that i.e. norm of T phi equal to norm of, okay, what is phi of, what is T inverse of phi naught? See, T inverse of phi naught, observe, is, see, suppose I start with the suppose T phi equal to phi naught. I'm saying if phi is in T inverse, if you have one phi in T inverse phi naught, then everything else is going to be obtained by phi plus m perp. If I take any two things which restrict the same functional on m, their difference must kill m. Right? So what they say that it is exactly the norm of phi. See, this is the norm in m upper star. I'm saying it's exactly the same as the norm of phi in x star mod m lower power. Right? This is what we've seen, right? That is, we've seen that in general x star mod m lower power is naturally identifiable with m lower star, with m upper star. This is just a Banach state. There is no dual, no pre-dual or anything like that. Okay, now if I want to go to m lower star, I observe that m See, what I want to say is that the same thing with lower star I want to say. See, T maps, see, you have this E upper star to M upper star, you have this mapping. And inside this you have E lower star, which by T goes to M lower star by definition. So this is what you have. And you proved that upstairs, if you take anything here, then the norm is identifiable with E. See what you have proved here is that is this statement with upper star in place of lower star.
that X star mod M cross is isometric with M star.
It is onto by definition, no? By definition of M lower star, it is onto. So I'm saying that this is, so I'm slightly waving hand, but I'm saying this shows that in fact one has that M lower star is identified with B lower star mod M per. The argument is exactly the same. You're taking this mapping T from M lower star to B lower star by restriction. It is a norm contraction. Its kernel is exactly M lower per, except M lower per is not in this. So I should say intersect B lower star. M lower per is not up there, but you're just intersecting everything with this. So I don't think I should waste more time on this. This is fairly simple-minded thing. And why is M lower star a norm-closed subspace? Because we've shown that you have this mapping, M lower star is isometrically isomorphic to B lower star mod the intersection of B lower star and M perp. See, B lower star is a Banach space and M perp is a closed subspace, and hence if you take the quotient space, that is also going to be a Banach space, and you've shown that that is isomorphic to M lower star, isometrically isomorphic. Consequently, M lower star is complete. So it must be a closed subspace of B lower star. Okay. And the final observation is that M is, did I say that there? That M is identifiable with, one is saying that M is identifiable with M lower star star. There is a natural pairing. M lower star sits inside B upper star, which acts on B and hence on M, and the kernel of that action is exactly that M perp intersects B lower star, and so it follows that I'm saying this also follows. So I haven't figured out the precise way of saying this, I haven't had time, but it is contained in everything I've said. You should be able to milk the fact that M equal to M lower star star. Then if you take anything in the dual of M lower star, it must be in the dual of, you made this identification. It must be in the dual of this. That means X star mod M perp is isomorphic to M upper star. That means this is going to be isomorphic to, so if it is in the dual of this, it must be in B lower star upper star, which is just B. Sorry, what am I saying? Which which is B. Why am I stumbling over this? Okay, I don't want to. Let's get on to less painful things. Paper on it. Vasant, can you get me some paper? I've got the wrong paper from my room. As soon as you enter, that red thing is there, no? Yeah. Thanks. Okay. So let's get on to the next theorem. So what we've really proved is that if M is a sigma weakly closed subspace of B of H, then let's write the following notation. Let's write M lower tilde is exactly all those omega span of omega c eta restricted to M. Okay. So these are the things that send x to xi eta. So you look at these linear functions, that is exactly the equal to WOT continuous functionals on M. Why? Again, by the same theorem we proved. You take an F and then you take the sigma BF, the continuous linear functions of that are exactly the things that come from F. So on M, if you look at the topology induced by these seminorms, then the only continuous linear functionals are the linear functions that come from these. You're doing this restricted to M, and the seminorm is given by just that. Vasant, you're looking huh? Okay. And M lower star the pre-dual in pre-dual. That is sigma weakly closed. The sigma weakly continuous. Functionals on it. Right, this is what we have been saying. So, okay. These are kind of trivial statements, so I'll just read them off. They say M rho tilde is nothing but the restrictions to M of things in B rho tilde. That is clear. And M lower star is the restriction of things, a restriction to M of things in B of H lower star, which is what I was waving my hands about. The proof is here in this thing. And that it is nothing but the closure of this M lower tilde. And that M is identified with this lower star, star and so on. Okay. And if C is a linear form on M, then C is sigma weakly continuous. On sigma in C in M lower star, if and only if C restricted to the unit ball of M is WOT continuous. Right? Everything that we said from B of H, one is just coming down to the subspace topology level. Okay, so let me not waste time on this proving this anymore. So this we'll take as done. So instead, let me just highlight some facts that are mentioned about these how many of you have studied no, not a fair question to ask. Okay, so let me just talk about this. See, we'll be interested in the case where M is a star algebra in B of H. And one of an algebras, I said, are things which are closed in any of these topologies. So, it is good to understand this. When you have a topological vector space, then you demand that the vector operations are continuous in that topology. Now here you have a topological vector space with this two additional structures. It has a product structure and it has a star structure. So you should worry about the compatibility of those two structures with the given topologies. So things are slightly delicate. So I want to observe that. Okay, and I want on B of H itself. So forget. So we'll be looking at this. So, but I want to consider the continuity of these operations in B of H itself. So I want to see whether these operations are continuous. Then if they are continuous in the big space, then on subspace with the subspace topology, they will also be appropriately continuous. So one wants to see on B of H. Let's look at multiplication. Is separately continuous with respect to SOT or any of these things. By that, what do I mean? I mean, if X alpha converges to X in any of these topologies, and if Y is something else in B of H, then X alpha Y will converge to XY and YX alpha will converge to YX in that topology. Okay. If you take SOT for example, what does this mean? You're assuming, see for SOT, what you're saying is that if X alpha psi converges to Xi for all psi, then you're saying that X alpha Y psi converges to X Y psi for all psi, or Y X alpha psi converges to Y X psi. The first statement is clear because it's true for all psi. It's certainly true for things in the range of Y. The second follows by continuity of Y. But and the same argument for the weak operator topology or sigma weak topology also. But I want to say that it need not be okay. But not jointly continuous with respect to what should I say? Any of these topologies actually. Yeah. Yeah. With respect to any of these topologies. So, example, you take U to be the unilateral shift, the right shift on L2. Operator theorists don't call this the right shift, they call this the unilateral shift because this is on L2 of n. The index set is taken as positive integers or non-negative integers. The bilateral shift is when you replace n by z, you take two by infinite sequences and you look at the shift. The two are different in character because the unilateral shift is an isometry but not unitary, whereas the bilateral shift is unitary. That is the basic distinction between them. Okay, now if you look at u power n, converges in the weak operator topology to 0. Okay, u power n xi eta. See, I'm just saying that if you take a sequence in L2, then see this is because, okay, maybe I should have said something else first. Okay, so before this, so I'll come back to this. I want to observe that the adjoint is WOT continuous. That is clear because x alpha converges to x means x alpha xi eta converges to x xi eta. If you take x alpha star, xi eta is by definition the conjugate of x alpha or something. So the adjoint is WOT continuous. So I'm saying that if you take u to the n star, then I'm saying actually this converges SOT to 0. If you take any vector xi and look at u to the n star of xi, what it does will be to kill the first n coordinates. And the L2 norm of u to the n star of xi will be the tail of that series defining the now square norm of xi. So that must converge to 0. So u to the n star converges SOT to 0, and hence also then u to the n converges WOT to 0. So u to the n star, which implies that u to the n also converges WOT to 0 because the adjoint is continuous in the weak operator topology. But clearly, if you take u to the n star u to the n, you get identity for all n. Which does not clearly does not converge to 0. So that at least I have shown you that multiplication is not jointly WOT continuous. So that is what I have proved. For SOT, one must do some more work. how does one see this quickly? Okay. However, I want to point out that on B of H1, if you take the unit ball of B of H, I want to say multiplication is jointly SOD continuous. It is not jointly WOT continuous because the U to the N and U to the N star all have norm 1. Norm 1 actually. And so it is not jointly weak operator continuous, but it is strong operator continuous. Now the reason is that I am saying if X alpha converges to X strongly, I'll just write S, and Y alpha converges to Y. I want to say that X alpha, Y alpha converges to XY. So here everybody has norm less than equal to 1 by hypothesis. So there is one epsilon by 3 or that kind of argument. Because you take X alpha, Y alpha, Xi minus XY, Xi. You want to make this small. So I've been through this kind of argument before. So you add and subtract many things. So X alpha, Y alpha, Xi minus, so X alpha, Y, Xi, if you wish, plus X alpha, Y, Xi minus X, Y, Xi. And then it is clear that X alpha, Y, Xi converges. The second term goes to 0 because X alpha converges to X strongly. And the first term, because the X alpha are uniformly bounded, the norm of this is bounded by Y alpha Xi minus Y Xi. And that goes to 0 by hypothesis. Right? So, okay. I want you to observe another thing. See, if a sequence converges to X strongly, actually if I write 1 or K also, the same thing is true. I just want them operators to be uniformly norm-bounded. So if we take a ball of radius K also, the same thing will be true. I'm saying if a sequence converges to X, that means Xn Xi converges to Xi for all Xi. That means that the sequence Xn Xi is a convergent sequence and hence bounded. Convergent sequences are bounded. Is bounded for all Xi. That means the Xn's are uniformly bounded in norm. Right? The uniform boundedness principle will tell you that sup norm Xn is finite. So this will already tell you that the weak operator topology is not metrizable. sequences are not enough to describe the thing, because you know that in the weak operator topology, multiplication is not jointly continuous. If the topology had been describable by convergent sequences, which is what will be the case if it's metrizable, that will tell you that multiplication should be jointly continuous. Because you've seen that on bounded states, multiplication is jointly continuous. And convergent sequences are uniformly bounded. So this shows that at least the weak operator topology is not metrizable. So you have to use nets when you deal with these topologies. It is just a fact of life. You must do this, which is why very often when you have theorems which say that see the theorem that is proved in this first chapter, I don't want to go back into the topology again, but which will say that if you have a sigma weakly closed subspace, or rather if you have a norm closed subspace, that will be sigma weakly closed precisely when its unit ball is sigma weakly closed. Why did I want to say this? So in order to show that if you have something, if you want to show that its space is if you have a space which is sigma weakly closed, like one Neumann algebra, then in order to verify that it is a one Neumann algebra, I have to only verify that its unit ball is sigma weakly closed. But on the unit ball, the sigma weak topology, the weak operator topology, everything is the same. And they are all metrizable. Is that clear? What is the weak operator topology given by? Is metrizable. Why? Because I can, I'm assuming, of course, I'll only deal with separable Hilbert spaces. H is separable, so I can take a bounded sequence, a dense sequence In and H in the unit ball of H. Right? Because this is equal to the weak on B of H is equal to, is generated by the seminorms P psi A is Ij. But these are dense. If I know that x alpha Ix Ij converges to x Ix Ij for all alpha, and I'm in the unit ball, because I guess I should have said this thing, right? So, because these things are dense, it will follow that, and the x alphas all have norm less than or equal to 1. It will follow that if x alpha P psi Ix Ij x alpha converges to the same thing of x for all Ij, they must converge for all xi eta. And the weak topology is given by a countable family of semi-norms, and if given by a countable family of semi-norms, then the topology will have a base of countable sets, countably many sets. So once you have, or you don't even have to do that, you can define a distance between x and y as sum over n, 1 sum over n m
Means separating
p xi m. If you take something like this, so then this will give you a metric on the unit ball, convergence according to which is the same as convergence against all these fellows. That means convergence in the weak cooperative topology. That means the weak cooperative topology is metrizable. The moment a seminorm, you have countably many seminorms given the topology, then it's a metrizable topology. Okay. So, what else should I say here? Okay, so I'll consider this first chapter as done and go on to the next chapter, which is, I think we've already covered most of it when we were talking about the spectral theorem before. So I'll just quickly run through this thing. So, the first observation he makes is that for any x in BH, so the statement is that B of H is a C-star algebra. That is, he is stating that norm of x star x equal to norm x squared. Okay, do I have to prove this, or you are, because you just have to take the soup over things given by such semi-norms. Right? This is going to be soup of norms I eta less than equal to 1. Blah blah, and which you can take this over there and then use Cauchy-Schwarz inequality. You will find that this is less than or equal to norm x squared. Okay. But why is it exactly equal to? We've done no. When you first apply this fact that the norm is given by the soup of such quantities, that will show that norm x star equals norm x. So this will show that norm x star equal to norm x. So first you show that the star is norm preserving, and then no, I should read this backward. The norm x squared I can write as actually, I can do it straight away. Norm x squared, norm x squared is actually also equal to this. Xi x eta. Xi it is a norm. Right? So straight away, anyway, this is something we all know, so I don't have to make a fuss about this. Okay, and then he says, so give the definition of an abstract C-star algebra, which we talked about. It's a Banach algebra satisfying the C-star identity. And for any x, he talks about, for any subset of B of H, you can talk about C-star algebra generated by that set. And that if x is self-adjoint, we know that C-star of x1 is identifiable with continuous functions on spectrum of x by an isomorphism which sends x to the identity function on the spectrum. And in particular, that says that if you take the norm of any f of x, so we have the continuous functional calculus for, so if x self-adjoint and f in C of sigma x, it shows that norm f of x equals, because we've shown that the functional calculus is star isomorphism, this operator norm in B of H is the same as the norm of f, the sup norm on the spectrum of x. Right? Okay. Okay, there's one theorem that I haven't. Did it talk about the spectral radius formula at all? Here. Have you seen that? Okay. So we define the spectrum of, in general we define the spectrum of x as all the lambda, where the definition of spectrum of x in B of H at least. And so the statement actually is that in any Banach algebra, unital Banach algebra, that's not necessary, but I just put it in. I define the spectral radius of x, which Stratila denotes by mod sigma x, which by definition is the maximum modulus of things in the spectrum. The spectral radius of x. The spectral radius formula says that this is actually equal to the limit as n goes to infinity norm x power n power 1 by n. Right? So this, at least some of you have seen this before, so I won't bore you with that. The actual proof is not so enlightening. The point to be made is that this sequence is actually convergent. The convergent sequence of non-negative numbers, so and that the limit exists, and so the limit must obviously be some number in 0, infinity. Because this is bounded by norm x. because of the submultiplicativity of the norm. Okay? So this also said that in any C star algebra, if X is normal, then it will tell you the norm X squared equals norm of X star X equals norm X squared. What am I trying to say? No. I wanted to say that where did I use? No. What I needed, okay. What I want is the following things. Okay, so let me back up for a moment here. So I want to observe that if what this so-called spectral radius formula tells you that in fact if A is commutative, mod sigma x is submultiplicative. Because if you take spectral radius of xy, you'll have the limit of norm xy over n whole power 1 by n. But because things are commutative, you can pull the powers of x and the powers of y separately and then use the submultiplicativity for x power n, y power n and 1 over n for the whole thing. And so you get this back. So that will tell you that okay, so this is equal to the spectral radius of x star x. We know this for self-adjoint x. Right? But if x is normal, then by what I know that this is less than or equal to mod sigma x star. But clearly mod sigma x star is equal to mod sigma x. Right? And this is less than equal to norm x squared. We know that. So I'm saying that this tell you already this spectral radius formula tells you that if x is normal, then also No, I wrote the wrong thing. I should have said. Yeah, okay. So it shows that if x is normal, norm x equals spectral radius of x. Yeah. But what I was actually you don't need this find, you can prove it directly. Remember I told you that if x is normal, an equivalent way of saying that is the norm of xi equal to norm of x star xi for every xi. From that it will follow the norm of x squared will be equal to norm of x star x. because if you take norm x star x xi, that is the same as norm of x squared xi, and then if you take the slope of the unit ball, you get these two things. And so I could have avoided this thing by just saying that this will automatically tell you that this is equal to norm x squared by the C star identity. And so, if this is true for 2, then it will be true for powers of 2 by induction. So, if you take that particular subsequence of powers of 2 here, there will be a constant sequence, norm x, and so it will show that this must be equal to norm x. And then this is a different proof of the same thing, without appearing to this. Okay. And we've done most of these things. It says if P is a polynomial, the spectral mapping theorem, spectrum of P of x equal to P of sigma x. If x is normal, then mod sigma x equals norm x. If x is self-adjoint, then sigma x is contained in R. And then this continuous functional calculus. For self-adjoint, we prove that continuous functions are the same isomorphic to C star of 1x. Okay, but maybe what we should do is so let me observe that if x is invertible, self-adjoint and invertible, then in fact C star of just x by itself will be that is the continuous functional calculus will actually map C of sigma x on to C star x. You don't have to separate it. See, earlier I'm saying C star x and C star x1 are the same. That is, I'm saying this is equal to C star x1 or equivalently that x star, that x inverse belongs to C star x. And hence the product 1 must belong to that thing. And for this you just approximate. If x is invertible, then the spectrum of x is away from 0. And 1 over x is a continuous function there. You can approximate with polynomials. And you can choose the polynomials to all have 0 term 0. If Pn converges to 1 over x almost everywhere, you can then so also will Pn minus Pn 0. and so, okay, so okay, now this is something I guess we didn't do, so I should. So I was saying that the advantage of the functional calculus is that it allows you to work with self-adjoint. We proved it only for self-adjoints now. Self-adjoint operators with as much ease as with continuous functions. That is, I'm for example, so assume X is self-adjoint. So then, what is the assertion is that there exists I haven't talked about positive. Okay, so have I talked about positive things here? No? Okay. No, we say X positive if the spectrum of X is contained in the positive line. Okay, then so the first assertion is that X self-adjoint implies there exists X plus or minus positive such that X equals X plus minus X minus and X plus X minus equals 0. Because you know that there is proof of continuous functions on the real line. As far as the C star algebra generated by X is concerned, that is identifiable with continuous functions on some compact set. There it is true that if you take f, and under the S morphism, X goes to f of t equals t. So, anyway, any real function can be written as f plus minus f minus, where f plus is the maximum of f in 0 and so on. Okay. X positive implies there exists y self-adjoint such that X equals y squared. This also but the same thing. As far as the functional, through the functional calculus, I identify this C star algebra with the algebra of continuous functions. And to say that I have a positive function means I have, so what is the spectrum of an element of C of sigma? The spectrum of a continuous function as an element of the C of sigma is just the range of that sigma under F. So to say it is positive means that it maps sigma to positive numbers. That means it is a positive valued function on the domain. In which case you can certainly write it as a square of a real function. In fact, you can not only choose a real function, you can choose even a positive function. Right? Okay, well, but the theorem is that X positive implies there exists unique positive Y such that X equals Y squared. See, so far, so this is in some C star algebra, right? X is in some C star algebra A. X is in B of H. Okay. It's a positive operate. Yeah, in fact, when you're talking about operators on Hilbert space, to say that x equals y squared will tell you that this is equivalent to x xi xi is greater than or equal to 0 for all xi. If we can write x as y squared, then I can take 1y over to the other side because it's self-adjoint, and then you get this positivity. Okay, see so far we were lucky in that we could do everything inside the C star algebra generated by X, which is a commutative object. So there's no problem with statements. So, but the point is that here, a priori, this y. Okay. Okay. So what do I want? See, first I'm saying that there exists something that I'll call x power half, which is the functional calculus applied to x. That is, take the square root function on the spectrum of x and apply that function to x. So, which is positive actually you don't even need 1 here. It is actually in C star x because the square root function vanishes at 0. So you can approximate by polynomials to vanish at 0, such that x to the half squared is x. So there is a square root, positive square root in this C star algebra itself. But now I'm saying more, I'm saying, okay, so I'm asking you to observe that. See, for uniqueness, I want to say anything, any y such that y squared is, any positive y such that y squared equals x must be in C star x and it must be this term. So you must force that commutativity. But that, so I'm just going to take 2 minutes to finish this thing off. So. So suppose y positive and x equals y squared. Then this is certainly in the C star algebra generated by y. Y is a self-adjoint, so it is the C star algebra generated by that y. But then x to the half is in C star algebra generated by x, which is contained in here. That means x to the half and y are both in the C star y, and they have square equal to x. But the C star y looks like a space of continuous function on some compact set. And in that context, it is true that if we have a positive valued function, it has a unique positive valued function whose square it is. Because for function spaces square roots of positive functions is unique. We can deduce from this that x to the half must be equal to y. Is forced to be equal to y. This is there is an important theorem. There is a fact that is used repeatedly, the so-called uniqueness of square roots. Okay. I would just worried to say that because okay. I didn't want to bring in my book and confuse the issue, but there are several examples discussed of continuity of these various operations in the various topologies. There is a section in my von Neumann algebras book which discusses these things, so you can. So I have a book called Invitation to von Neumann algebras. So in that there is a chapter where all these things are discussed. As soon as the topologies are defined, and one discusses all the continuities of all these operations.